something down on top, you close the cover, you say scan, you send it a command from your computer, and there's a bar inside, like in a Xerox machine, that moves across the bed, and at each point it shines up on the piece of paper, it picks up what's reflected, and basically gives you a set of ones and zeros, which tells you where there's dots along that particular line that it's scanning. Okay, that's a simplified version. Ignore color. So you want to use that to compute logarithms or cosines for their scientific functions. Okay, desert island. Make yourself a piece of paper. You get some berry juice or something for drawing, and you draw yourself a sine wave. Okay, and there's all kinds of ways to draw sine waves with circles and string. They pop up in nature all the time. And let's make this 360 millimeters. Okay, it's about 14 inches, typical size for a legal size scanner. Now you take this and you put it on top of your scanner. And now you want to compute the sine of 140 degrees. Well, you send instructions to your scanner which says move the scan bar 140 millimeters from the edge. So now you have this thing that emits light and detects reflected images 140 millimeters from the end is sitting right here. And now you say turn on the light and see what's reflected. And it will, assuming you use a nice clean white piece of paper, it will see exactly one dot sitting right here. Everything else is white. And you look at the position of that dot, and that's the sine of 140 degrees. And if you want to compute cosines or logarithms, you just take a different piece of paper, put it on your scanner, and you do the same thing. Okay, this is just another lookup table. It's a physical lookup table, but it's still just another way of storing input to output mappings. So using a piece of paper and a scanner, you can store a single y equals a function of x and y. Are you familiar with some of the older technologies in the 30s and 40s that were used for memories? Because transistors didn't exist and vacuum tubes were really expensive.
There's something with wires crossing each other and they touch, they pin them together somehow.
Mm-hmm. There was an old scheme that had basically pairs of wires crossing each other and a small metal donut sitting at each junction. A little metal ring, ferrite. And by putting current through these, you could magnetize these little donuts, one orientation or another. And you could actually store ones and zeros in that way. Okay, they actually took old pill-making machines and modify those to press out these little tiny donuts with holes in the middle to make these things. This was called a core memory. So when you're on your computer and it says core dumped, that's what it's talking about, dumping the core memory. That was a really early version of random access memory. There were some even stranger techniques that were used. There was a system that was popular where so old style TVs have a cathode ray tube, and the surface is covered with a phosphor, and if you shoot a beam of electrons at it, it lights up. And when you turn off the electrons, that lit spot slowly fades away. And by scanning that and turning it on and off, you make a TV image. You can actually use that for storage. you could shoot a beam to turn on a particular pixel on your display, and then you could sense it. And if you wanted to write a 1 in a particular position, you would simply turn that on, and then you would have a sensor that would say there's a pixel lit up there. And you could use that as a random access memory. And you just needed to refresh it periodically before that dot faded. You would find every spot where there was a dot, and you turn the beam back on. So there were CRT-based memory systems. Another way to store memory was acoustically. When I was a kid, I had a guitar I used to mess around with, and I got an echo box for it once. And the echo box basically consisted of a spring and a small speaker on one end and a microphone on the other. And you agitate the spring with the microphone, and it would take a second or two for the signal to move down this spring and hit the other side, and you'd get a delay. You can make an echo out of it. But you can actually use that to store information. You can put in a signal and you can code this as 0, 1, 0, 1, 1, 0. And it's how magnetic tape stores information. You can code a set of 1s and 0s in an analog signal, and if you put this into a delay line, it'll take a few seconds to reach the other end, and you can take what's coming out of the other end and feed it back in and preserve this pattern of 1s and 0s and actually store information on that. And you can do it with a spring. They used to use it with, they'd use cylinders filled with mercury in liquid form, and they could pass a small wave through it, and they could actually preserve it. And mercury delay lines were another common storage technique.
But they just put a positive feedback amp and just keep it ringing?
You could.
I mean, is that the idea? They just keep it...
But how do you build an amp?
Oh, right.
Right, so this is like 1930s maybe.
Right.
And vacuum tubes were expensive. But I mean, you did need amplifiers for this because you needed to take the signal coming out and refresh it back to full strength. Okay, so the reason that this has anything to do with computation today. So using that flatbed scanner, you can store a function y equals f of x and read it back, but it's hard to modify it, okay, because you have to change this piece of paper. But using something like a mercury delay line in an acoustic memory system, you can actually feed in not just a binary signal, but a continuous valued signal, such as a simple sine wave. And if you took that, used it to put a pressure wave into a tube of mercury, read it out from the other end, you can actually store this entire function, y equals sine of x, in a memory. So it's a non-digital memory. It's a continuous valued memory of one variable, y equals some function of x. Okay, what if you wanted to do function of two variables? Can you think of any way to store that in a physical lookup table?
Separate the lookup table into multiple parts, and then the first one will address which part, the second one will address which line.
You can do that to some degree. The problem is that you can do that if these are discrete values. Okay, if you only had 4 values for x, 4 values for y. But when these are continuous values, when you want to be able to take in any number, say between 0 and 1, you need something higher dimensional.
Well, if there are 2 different colored lines, you could do it that way.
Well, if you add a second line, that would let you do that would let you store 2 different functions.
I see. Right.
Same with breaking up a truth table. But if you actually want 2 inputs, okay, there's one way I know of to do it, although it's not very practical. But think of a drum head, okay, a piece of elastic, 2-dimensional, stretched over some sort of boundary. Let's make it a square drum head. And you can think of your position as X and Y from some lower left corner. And when you hit this drum, the surface begins to deform. Okay, it changes its height, its Z value. And so at each point X, Y, you have some function which tells how high that membrane is relative to where it is at rest. Okay, this is a way that you could store a two-dimensional function. You could make a rigid mold in 3D, and you want to know the value at some point X, Y. You move over X, you move up Y, and you look at the height of the surface at that point, and that tells you the function value. Okay, so that's a way to do it. Again, it's hard to write. But it's a way to store information, at least for a 2D function. Okay, what about 3 variables?
Combination line.
You could.
I think that would work, actually.
How so?
Because the way they work inside.
So remember, X, Y, and Z are continuous values.
Yeah, because, well, yeah. I mean, it limits you to whatever. I mean, I guess you can subdivide 360 degrees by as many as you want, but you're always operating in a circle. But it moves one tumbler a certain amount, and then it basically you come up with any combination of tumblers in there, so that would define the function of 3 variables, could you?
I'm not sure what the logic would look like.
Yeah, I'd have to think that. I'm not willing to stand behind that yet.
Okay.
Too early.
One example I've thought of for how to do 3 variables. Take a 3-dimensional space like this room. Okay, X is how far over you move, Y is how far out this way, and Z is how high from the floor. And at that point, somehow have the temperature set to a certain value. Okay, or the air pressure, or some other characteristic. And assuming you control and hold the temperature at different points to different values, you could store a function of 3 variables in, say, the temperature of the room inside a 3D space. Okay, that one's even less practical. That one I don't know the answer to. I think if you figure that one out, there's like Nobel Prize material there, though. This is the key to building a different type of cell matrix in 3 dimensions. And it's a very powerful one. We'll talk about it in a week or two. This will be a continuous valued cell matrix. And it requires being able to physically store a 4-input lookup table, preferably in a way that can be rewritten easily. So that's another background question to ponder. All right, that's all I was going to say today. I'll figure out my laptop by Wednesday and go over a little bit about homework 2 and some of the examples, and we'll talk a little more about wire building and see where that goes. I'm not going to have class on Friday, okay, so Wednesday and then nothing until next Monday. All right, thanks.